Hello, in this video I'm going to be explaining the relationship between the adiabatic saturation temperature and the wet bulb temperature. So in this problem we have an infinite tube, and we know that the infinite tube is going forever and it is perfectly insulated. So there's no heat or cold air that is coming through the system. We have a mass flow rate of air that's entering at a temperature and a partial pressure of the water. And at the outlet stream, we have a temperature that is going out. And so we know that this tube is infinite. We know that it is going to be evaporating at the end. So we have a saturation temperature of the partial pressure of water at the temperature of water. So what we're going to first need to do in this problem is we're going to be making an energy balance. And we're going to be, first, we're going to write an equation for the enthalpy that is going into the system. So we have a mass flow rate of air that is entering. We have the heat capacity with the temperature of the inlet plus the heat of vaporization with the partial pressure of water multiplied by its molecular weight over the gas constant times the temperature. We're going to multiply that again by the gas constant over the temperature, over the total pressure, and the molecular weight average. And we're doing this because we want to get this in kilograms per meter cubed. So we have the enthalpy in. Now we need to write an equation for the enthalpy out. And then set them equal to each other because this is going to be a energy balance. So the equations are going to be very similar. We have a mass flow rate of air that is entering the system, the heat capacity multiplied by the temperature out, and we said the reference temperature, we're going to say that T reference is going to be equal to 0, so T minus in minus out, so we can just say it's 0, so we can just write T in, and then we can just write T out. So we're going to add that by the heat of vaporization multiplied by the saturation temperature of the water at the temperature of water multiplied by the molecular weight over the gas constant times temperature, gas constant times temperature over the P total, and the molecular weight average. So now that we have our enthalpy in and enthalpy out, we want to set it equal to each other. So before we even set them equal to each other, we can see that the gas constant and the temperature all cancel out. So M air multiplied by the heat capacity, Tn, temperature in of the inlet, plus the heat of vaporization over the partial pressure of the water over the molecular weight over the P total and the molecular weight average. And then we're going to set that equal to the M air. It is this one's going to be C, the heat capacity, multiplied by the outlet, plus the heat of vaporization of the saturation temperature of the water at the temperature of water, multiplied by molecular weight over the P total, and then molecular weight average. So from this we can see that the mass flow rate of the air coming in cancels out, so don't have to worry about that. And we're going to rearrange this equation. So we're going to say that the heat of vaporization and the molecular weight over the total pressure and the molecular weight average. And we're going to say the pressure of the water minus partial pressure of the water minus the saturation pressure of the water at the temperature of water. That's equal to the heat capacity and then the temperature out minus the temperature in. So we're able to find an equation for the adiabatic saturation temperature And we want to compare it to the wet bulb temperature that we found in the previous video. So as you can see, this is the adiabatic saturation temp, and this is the wet bulb temp. So we can see how similar these equations are. If we subtracted it throughout the second equation, we can see that these are flipped and these will also be flipped. We can also see how